Hello friends, we are discussing approximate methods for the solution of radiative transfer equation. In the same category, today we will discuss the method of spherical harmonics, that is P-n approximation method. As discussed last time, the approximations in the solution of radiative transfer equation may be threefold. In the first category, we simplify the geometry of the problem. So, we try to solve radiative transfer equation for one dimensional medium, either the plane parallel slab or the cylindrical medium. In the second category, we approximate the properties of the absorbing medium, that is, we assume that the kappa or the absorption coefficient is very small, optically thin case, or it is large, optically thick case. Today we will discuss the method of spherical harmonics, and this method is basically the third type of method, where we basically divide the intensity or approximate the intensity in directions. So, let us suppose at any point in the medium we have actual intensity distribution which may not be symmetric. So, the intensity can be divided into two parts, the one component moving in the upward direction and the second component moving in the downward direction, and it may not be symmetric or isotropic at all. We saw for the case of two approximate methods in the last class, that is the Schuster-Schwarzschild approximation two flux method and Milne-Eddington method, that is the differential approximation method. The intensity distribution was assumed to be isotropic with different magnitude in the upward direction and downward direction. So, we assume that the intensity is isotropic, but the magnitude of intensity in the upward direction is different, and the magnitude of intensity in the downward direction is different. So, this was assumed for the two methods that we discussed in the last class. Now, the basic idea of the method of spherical harmonics or P-n approximation method is similar. We have to define the directional dependence of intensity. The advantage is similar to what we get in the two flux method or differential approximation method, that is our integral differential equation is converted into a set of differential equations, and the P-n method is very popular. It is implemented in many commercial codes like Fluent and Star CCM. The reason is that we know how to solve these differential equations, and it can be easily implemented in CFD codes. So, we start with the idea of the spherical harmonics. So, most of us are comfortable and familiar with Fourier series. So, if in Fourier series we have circular functions like sines and cosines, and with the help of these circular functions we use these circular functions in a form of series to represent any function. So, Fourier series is defined in two dimension circular functions like sines and cosines, and as a series of the sines and cosine functions we can write any function f x. Okay. Now, in 3 dimension on the surface of a sphere, which basically we want to represent our intensity, we use similar representation, and this representation is called the spherical harmonics. So, spherical harmonic series basically is used to represent intensity in the 3 dimensional space on the surface of a sphere, and this, as we will see, satisfies the Laplace equation in spherical coordinates. So, before I go into the details of the method of spherical harmonics, if we can understand clearly how the Fourier series is used to represent a function, it would be easy for us to understand the method of spherical harmonics. So, on this slide you see a sine and cosine series representing a square wave. So, we have a square wave and if we use only first term of the series, so we have an infinite series, or the series may have n terms. So, the function is periodic, that is the square wave is a periodic function, and this periodic function we want to represent using a series of sines and cosines. So, if the first term is retained, we see that we get a sine wave, and the sine wave is not able to fit the square wave very accurately. If we take two terms, we get a better agreement, and this wave agrees or represents the square wave much better than the single term of the series. We keep on increasing the terms in the series, and our result gets better and better in agreement with the square wave. So, this is how basically we can represent a function f n x, a periodic function f n x, where n subscript n represents that there are total n terms that have been taken in the series, and this function which represents the square wave in this example is used to is represented by this form of series, and this series is called Fourier series. To give you a clear idea why this is called circular function, what you see on this slide is basically the variation of the y magnitude of the wave as the pointer moves on the circle. Now, the pointer speed along the circle is changing. So, here we have the rotation at sin theta upon pi, here we have sin theta, and so on, and based on the speed of the rotation, the wave is better able to represent the square wave, and we see that if we can combine one or more two or more terms of these circular functions in a series, then the function can be represented very accurately. So, this is in 2 dimensional space, and we are representing a function using circular function. Now, intensity we understand is a 3 dimensional quantity, that means the intensity varies over the entire solid angle 4 pi, and it varies on the surface of a sphere, that means we represent it using spherical coordinates. So, we can, if we can represent this intensity in the form of a series just like a Fourier series, we probably can convert our integral differential equation into some form of differential equation. So, this is basically the idea. Now, first of all we will understand what is spherical harmonics, and then we will go for how the spherical harmonics can be used to solve the radiative transfer equation. So, in spherical coordinates, the Laplacian of a scalar del square f, where f is now a scalar function. So, intensity is the not a scalar function, it is a vector function, but let us understand first for the scalar function. So, Laplace of a scalar function del square f in spherical coordinates depends on its coordinates r, theta and phi. So, it can be written as 1 by r square del by del r square del f by del r, plus 1 upon r square sin theta del by del theta of sin theta del f del theta, plus last term 1 by r sin theta square del square f by del phi square, and this will be equal to 0. So, in spherical coordinates this is the Laplace equation, and the solution of this Laplace equation will basically contain or comprise the spherical harmonics. So, using the method of separation of variables, we can solve this equation in spherical coordinates. We will have a term that will be purely dependent on r by the method of separation of variable, and one term which will be purely dependent on direction. Now, direction contains both theta and phi. So, we have what we call method of separation of variable solution for this type of problem. Okay. Now, the second term that depends on direction is called the spherical harmonics. So, this term is basically the spherical harmonics, and how they look like. If you plot this function, the spherical harmonic function, it has a familiar shape that you must have studied in 12th class, which has shapes like SPDF orbital shapes in chemistry. So, the first term of this series of YLM, that is if L is equal to 0 and M is equal to 0, the first term of this series has symmetric shape, that means it does not depend on theta or phi, polar and azimuthal angle, and the shape is spherical, and in chemistry it is called s orbital. Similarly, the second term L is equal to 1 has 3 values. The values of m will be 0, minus 1 and 1 for L is equal to 1. So, for each value of L there will be 2L plus 1 values of m, and the shape is like p orbital shape. So, there are 3 and the shape is of type p orbital in chemistry. If you go for higher order terms, L is equal to 2, the shapes are of d orbital, and there will be 5 terms, and similarly there will be 7 terms if you go for L is equal to 3, that is the f orbital. So, L is equal to 0 is s, L is equal to 1 is p, L is equal to 2 is d, and L is equal to 3 is f. So, what does it represent? If we take only one term in the series of spherical harmonics, that is only one term in this equation is taken, then we are assuming that the intensity is going to be isotropic. That means intensity does not depend on theta, does not depend on phi, it is independent of polar angle and azimuthal angle. If we take two terms, first and second term, then for both the terms the azimuthal angle does not appear. So, the second term, the intensity variation that looks like p orbital is a function of theta only, it does not depend on azimuthal angle phi. So, idea here is that if we can represent intensity as a series of these type of functions, then we should be able to capture the effect of intensity variation much more accurately than what we have already done in the case of two flux approximation or the differential approximation. So, the solution of YLM, the term YLM looks like this expression, and this can be easily derived by applying the method of separation of variables. It contains the value of L and M, where L is the degree of the spherical harmonics function and M is the order of the spherical harmonics function. So, L and M represents the degree and order of the spherical harmonics function. In chemistry they have their own meaning as angular momentum and magnetic moment, but here L is basically defines the degree of the spherical harmonics function and M represents the order of the spherical harmonics function. It has dependence on polar angle cos theta, and it has dependence on the azimuthal angle psi. Here just do not get confused with the notation, basically phi and psi are basically the same here. Sometimes we use phi in the spherical harmonics function. So, spherical harmonics functions are used to represent the intensity just like Fourier series. If we just retain the first term, then L is equal to 0, M is equal to 0, and we get YLM, the angular dependence of intensity is 0, that means intensity I is isotropic for the first term. And if we take the first term, then L is equal to 1 and M is equal to 0. From this equation just substitute L is equal to 1 and M is equal to 0, and you will get YLM, that is angular dependence of intensity, as P10 cos theta or simply cos theta. Now, what is P here? P is basically the Legendre polynomial. Okay. So, P01 and cos theta is the argument. Okay. So, PLM is basically associative Legendre polynomial. So, this is the associative Legendre polynomial, and it has again PLM is the degree and order of this polynomial, and the first value for L is equal to 1 and M is equal to 0 is simply, and x is the argument. Okay. So, this is the function, Legendre polynomial is a function in variable x, and the P10 value is basically given by simply x. So, PLM root cos the argument cos theta is simply equal to cos theta. So, the second term depends on cos theta, and this variation, if we plot the variation of this term versus theta, the shape will look like that of a p orbital, that is like this, and what it basically says is that the intensity variation is following a distribution of cos theta, and it does not depend on azimuthal angle, and we see that there is very little intensity in the grazing angles. The maximum intensity is in the normal direction and the intensity decreases. So, the intensity is maximum at theta is equal to 0, and for theta is equal to 90 degree the intensity is 0. So, this is the one term, okay, but there will be similar terms in y and z coordinates also. So, we will have 3 such terms, and all these terms are then added together in the Fourier series. So, the Pn approximation method, where n means how many terms in the Fourier series actually are retained. So, we have written the intensity, that is the intensity variation at any point in the space will be function of radius r and direction s, which where direction depends on theta and the azimuthal angle psi, and which can be written in terms of a series or spherical harmonics. Now, if we retain the terms for L is equal to 0 and 1, the method is basically called the P1 approximation method, and if we retain terms for L is equal to 0, 1, 2 and 3, that is up to order 3, the method is called P3 approximation method. So, depending on what is the largest value of L retained in the series, the method is called by the largest value used. So, if 1 is the largest value of L used, it is called P1 approximation. If 3 is the largest value used, it is called P3 approximation. Now, let us substitute this intensity which is approximated as a series of spherical harmonics into the radiative transfer equation for isotropically scattering medium. We know the governing equation is given by this equation. So, in this equation we will substitute for the expression of intensity in the form of series, that is we will put this expression. Here we will make one simplification. If we are using P1 method, we have already observed that the intensity has no dependence on azimuthal angle, and if we take a special case of one dimensional medium, then also the intensity will not be a function of azimuthal angle. Okay. So, the dependence on m will basically drop down, and we can simply write down intensity which will be a function of now tau and mu only, that is polar angle and space coordinate tau, and we can write down in a simplified form the same series of spherical harmonics as IL tau PL tau, where PL is basically the associated Legendre polynomial. Now, these polynomials we observe have a special property. This observes the polynomial Legendre polynomial, they have a property of orthogonality. That means, for different values of L, that is if we take one value P L mu and other value P M mu, L and M not same, then their integration P L times P M over the argument d mu will simply be equal to 0. So, this is the orthogonality property of these special functions, and if the value of L and M are same, then we get the value of the integral as 2 over 2 m plus 1. So, we substitute the expression of intensity in the radiative transfer equation, and what we get is this equation. So, d summation L is equal to 0 to n d I L by d tau mu times P L mu plus I L tau P L mu, and right hand side 1 minus omega I b tau plus omega I naught P naught mu. Now, this is under the assumption that we have isotropically scattering medium and intensity is function of tau and mu. So, we have reduced the integro differential equation into a simple differential equation. Now, we have n unknowns, n plus 1 unknowns in this expression, starting from P0, P1, P2 and Pn. So, unknowns here not P0 rather I0. So, unknowns are I0, I1, I2 and so on up to In. So, there are n plus 1 unknowns in this expression. Now, we have to find out n plus 1 equations to solve this for these n plus 1 unknowns. So, what we will do is we will make use of the orthogonality property of the function. Now, before we apply the orthogonality property of the function, we have to get rid of this term mu times PL mu, because if we do not get rid of this term, we cannot apply the orthogonality property. So, we will use the recursive property of the Legendre polynomial, associated Legendre polynomial, that is 2L plus 1 mu times PL mu is L times PL minus 1 mu plus L plus 1 PL plus 1 mu. Now, orthogonality property can be applied on the terms on the right hand side, but cannot be applied on the left hand term on the left hand side. So, we will replace the term in the RTE with this using the recursive property, and then we apply the orthogonality property. We multiply the entire radiative transfer equation by pk mu and integrate over all the solid angles. So, some of the terms will cancel out as per this relation. For terms where we have L not equal to k, the term will be 0 and some terms will be retained. The final equation for radiative transfer equation for Pn method will be given by this equation. So, we have two derivatives in this term, dik plus 1 d tau and dik minus 1 d tau, and then we have ik also. So, this is the governing equation for Pn method and this is a differential equation. So, we have removed the integral from this equation and we have got a simplified differential equation. Of course, the number of unknowns have increased, but we can still solve it for any problem relatively easily. Now, we will take a special case, that is P1 approximation method, which is mostly used in radiative heat transfer community. So, most of the commercial softwares like ANSYS and Star CCM, they come up with this P1 method. In P1 method, the values of L retained will be 0 and 1. So, two terms will be retained. The first term I0 Y0 and the second term will have three components. For L is equal to 1, M is equal to minus 1, 0 and 1. So, there will be four terms. The first term will be represented by intensity, which is isotropic. The second term will have intensity like this and similarly in other direction. So, there will be three terms of three different intensity variation. Now, we apply the method the Pn solution, and for this special case we substitute k is equal to 0. So, in this case we will have k is equal to 0 and 1. We will get two equations. The first equation we substitute k is equal to 0. So, we get 1/3 d I1 by d tau plus 1 minus omega I0 is equal to 1 minus omega IB tau. So, this is the first equation, and then the second equation we get 2/5 d I2 by d tau plus d I0 d tau plus I1 is equal to 0. Now, since we have retained only two terms I0 and I1, d I2 by d tau is equal to 0. So, we get, so this is equation 1 and this is the equation 2, d I0 by d tau plus I1 is equal to 0. So, this is the two equations for the P1 method. We also can easily establish that incident radiation G is related to the first term I0 4 pi I0 and the heat flux is related to the second term 4/3 pi I1. So, this equation, the first equation we can replace as dq by d tau plus 1 minus omega g is equal to 4 pi 1 minus omega IB tau, or taking that g term on the right hand side we get dq by d tau is equal to 1 minus omega 4 pi IB minus g. So, this is the first equation, and we have found that for two flux approximation also we got the similar equation. The second equation we multiply by 4 by pi 3, and when we do that we get the second equation as 1 by 3 dg by d tau plus q is equal to 0. See, these are the two equations for the P1 method. So, we get two equations, two differential equations for the P1 method. Now, we have derived this for one dimensional case, but the method is not restricted to one dimensional case, it can be extended easily to higher dimensions. The only thing is we have to replace the derivatives appropriately. The boundary conditions for the P1 method can be written as intensity at the bottom wall for this one dimensional medium. So, we have one dimensional medium. For this we want to write down the boundary condition for the P1 method. Okay. So, please remember, in two flux approximation method we assume that the intensity is isotropic at the wall. So, this was the assumption we made in the two flux approximation method as well as differential approximation method, but here we cannot take intensity to be isotropic because we have written the intensity inside the medium with spherical harmonics. So, inside the medium the intensity is varying as per the spherical harmonics. So, at the wall also we should not take it as a isotropic. So, rather the intensity is defined as a function of mu. Okay. So, intensity at the bottom wall depends on mu and intensity at the top wall depends on mu. Okay. Now, what kind of dependence will be on the mu, that is the polar angle, we will see. So, there are two ways of doing it, how the intensity varies with polar angle at the wall. The first is given by Mach. Mach's boundary condition says that it is not possible to represent wall intensity in all the directions. So, what Mach proposed is that along some discrete directions, let us say mu I, we have represented the intensity at the wall correctly. So, in Mach's boundary condition the intensity is represented by discrete values in discrete directions correctly. So, I 0 at a discrete direction mu is equal to mu I, the intensity is IW1 mu I. So, that means if you have actual intensity, only in discrete direction we have applied the intensity, not in the entire solid angle 2 pi. Now, for n is equal to 1 we will have only one direction, for n is equal to 3, that is P3 approximation, we will have two directions. Okay. Now, in Mach these directions are basically defined by Legendre polynomial, and the value of mu comes out to be 1 by root 3. So, the boundary conditions now becomes I 0 0, that is the bottom wall, plus I 1 0 by root 3 is equal to I b 1. So, this is the first boundary condition at tau is equal to 0, and the second boundary condition is in the direction mu is equal to minus 1 by root 3 and I naught tau L minus I 1 tau L by root 3 is equal to I b 1. This is the second boundary condition at tau is equal to tau L. So, boundaries are still the problem. We have tried to accurately represent the intensity using spherical harmonics inside the medium, but at the wall we have to satisfy certain boundary conditions, and these boundary conditions are approximate, and in this case only one direction, in only one direction we have represented the intensity. The other concept in boundary condition is given by Marshak. Now, what Marshak argued, that instead of representing boundary intensity in a discrete direction as was given by Mach, we should satisfy the wall intensity at the boundary in an integral sense. So, what he did is basically he took the intensity at the wall multiplied by the Legendre polynomial and then integrated it, and he argued that this intensity should be satisfied. So, based on the value of intensity coming from the wall, that is IW1, and this is the intensity coming from the medium or going into the medium, the two should be satisfied at the wall in an integral sense. So, when we do that for the top, bottom and top wall, the boundary conditions becomes I 0 0 plus 2 I 1 0 by 3 is equal to I b 1. This is the first boundary condition at tau is equal to tau 0 is equal to 0 rather, and the second boundary condition I 0 tau L minus 2 I1 by 3 is equal to IB1. Okay. So, there is slight difference in the boundary conditions. If you look here, we have I1 0 root 3, I1 tau L root 3, here we have 2 I1 by 3 and 2 minus 2 I1 by 3. So, this is how the boundary conditions between Mark and Marshak have changed. Again I will highlight the difference between the two boundary conditions. One is based on discrete direction. Mark says that intensity at the wall can be specified or satisfied in only discrete directions, and in P1 case it was only single direction, in P2 P3 case it was two directions, while Marshak said that the intensity at the wall should be satisfied in an integral sense. That means the total integral of the intensity should be satisfied, and based on that we get this boundary condition. So, we will do some problems in the next lecture, and I will also introduce you the other aspects of this method, the spherical harmonics method. Thank you.